What if I told you that one architecture changed the entire AI landscape, making GPT, BERT, and almost every modern large language model possible? That architecture is the transformer. Today, we're diving deep into transformers, explained simply and thoroughly. Before transformers, AI relied heavily on RNNs and LSTMs for sequence modeling. These models struggled with long-term memory and slow training. In 2017, the paper "Attention is All You Need" introduced the transformer, and everything changed. So why are transformers so revolutionary? They removed recurrence and convolutions, replacing them with self-attention. This allowed models to process sequences in parallel, capture long-range dependencies, and scale massively. At the heart of transformers is self-attention. Think of it like reading a book. Instead of just focusing on the next word, you can instantly recall and connect words from any part of the sentence. That's what self-attention does. Finds relationships across the sequence instantly. Technically, self-attention works with queries, keys, and values. Each word is transformed into vectors. By comparing queries and keys, we compute attention scores, which weight the values. This gives us context-aware representations of words. But wait, self-attention isn't just single-headed. Transformers use multi-head attention. Think of it as multiple people reading the same book, but focusing on different patterns, syntax, meaning, and context, all at once. The outputs combine for richer understanding. One challenge: transformers don't naturally understand order, since they process everything in parallel. The solution is positional encoding, adding patterns to inputs that represent sequence order, like rhythm in music guiding notes. Now let's look at the transformer structure. It has two main parts: the encoder and the decoder. The encoder reads and represents input sequences, and the decoder generates outputs step by step with help from attention on the encoder. Training transformers requires huge amounts of data and compute. They use techniques like teacher forcing, masked language modeling, and autoregressive training to learn powerful representations. This is why models like GPT and BERT became possible. Transformers aren't just for text. They're everywhere, in vision models like vision transformers, in audio models for speech recognition, in protein folding research, and even in reinforcement learning. They're the Swiss Army knife of deep learning. Compared to RNNs and CNNs, transformers are faster to train, better at scaling, and capture long-range dependencies. This makes them the backbone of modern AI models, especially large language models like GPT. Large language models, or LLMs, like GPT-4, are all built on transformers. By scaling up the architecture with billions of parameters and massive datasets, we get AI that can write, translate, reason, and even chat with us. Of course, transformers aren't perfect. They're extremely compute-hungry, require massive datasets, and sometimes hallucinate. Researchers are working on efficient transformers, retrieval-augmented models, and hybrid architectures to overcome these issues. The future of transformers is exciting. With innovations like sparse attention, efficient scaling, multimodal models, and agentic AI, transformers are likely to remain at the core of AI for years to come. And that's a deep dive into transformers. From self-attention to powering the largest AI models in the world, they've reshaped the AI landscape forever. If you enjoyed this beginner-friendly deep dive, make sure to like, subscribe, and join me for more AI explained simply.